So let me first introduce myself. My name is Mykola, and I'm an embedded developer at FLab. Um, Originally, I'm from Ukraine, but I'm living and working in Italy. And I got into embedded systems a few years ago. I already have some experience, but I'm still learning, and I would like to share with you some of the things about embedded systems that I find really interesting. So first, let me see. First of all, let's see what an embedded system is. So essentially, an embedded system is a combination of hardware, software, and some additional components specifically designed for dedicated function. It is actually, it combines a microprocessor just like any computer does. It has some memory and it has some input-output peripherals that we will get into in the next slide. Interesting fact is that in 2009, it was estimated that pretty much, it's a crazy number, 98% of all microprocessors were using embedded systems. So if you think about, you always hear about Intel releasing its new processors, or AMD, or maybe perhaps NVIDIA cards, but those are actually just one small part of the total market of microprocessors which are being used. So the first modern, let's say, embedded system was Apollo guidance computer, and it was responsible for collecting information and guiding basically the rocket, steering the rocket, and making sure everything works correctly. It was drastically different than more modern microcontrollers by a long stretch. And I think, like, if you're interested, just to Google about this, it's a pretty fascinating piece of engineering in itself. So there are different types of embedded systems, and here is an attempt to categorize them. So they can be divided based on performance, or on the tasks that they do. They can be real time. They can be standalone, network, mobile. They can be more powerful, more small scale, large scale. So pretty much anything you can imagine. And there is a brief summary of some of the embedded system devices. And what's really fascinating is that, like, they are all over, like, all around us. They are used in all kinds of. You probably in your daily life, you use a lot of devices that you don't even suspect have microcontrollers or microprocessors embedded inside. So they have drastically transformed how we live and how we interact in our daily lives. It might be interesting to compare general purpose PC with an embedded system, and just to highlight some of the differences. So the, I guess, most apparent difference is that embedded systems, they are meant for some single purpose, single function. I mean, typically, while general purpose PCs, they are multifunctional. You can do all sorts of things. They are great at interacting with people, while microcontrollers, they are really designed to interact well with external world. Um, um, General purpose PCs have unconstrained resources, right? They can have terabytes of memory, they can have lots of RAM, while embedded systems usually have maybe 30 kilobytes of RAM and perhaps 500 kilobytes of flash or less. The general purpose PCs, they are not great at real tasks, real-time tasking, while embedded systems are, and they are much more reliable. So an example is a microcontroller. It has like different internal components, some that PCs do not have. They have different interfaces, SPI, USB, I2C, which are used to interact with other small devices. So they are, in this regard, very different. In terms of programming, they are programmed in C or C++, since it's the most effective way, efficient way to do that. There is also MicroPython been introduced in the recent years, but it's a lot slower. And but given that microcontrollers become more and more powerful, this might gain some traction. In terms of programming, like approach to programming these devices, you can have several ways. There is a bare metal approach. There is real-time operating system that can be running in these devices, and well, you can of course run the next one on a microcontroller, but full-fledged OS is even a further abstraction step towards programming such systems. Well, I should say that in some cases you can actually run, a full-fledged OS on a relatively on a what you would consider even a microcontroller. So bare metal, you essentially write your own operating system. You have to really manage all the flow of the application, and be very meticulous in designing how different how your application operates. But this is the probably most efficient way, which requires least resources to program such devices. Real-time operating systems, they allow to basically work more efficiently with in terms of running a lot of tasks on a microcontroller. So they sort of provide like a concurrency of execution of different things. They separate you from hardware somewhat, but they're still very lightweight, and most importantly, they do, as they are named, provide real-time operating functionality. So it means that your tasks will be always, or at least in most cases, will be executed not later than a certain deadline, versus normal operating system where you can't really have that guarantee because there is just too much software layers, and the kernel is not designed in a way that that has this guarantee. You might be wondering how to get started with all of this, and I'm sure that all of you have heard about Arduino. It's pretty infamous these days. It's very easy to use. It has an integrated environment and lots of libraries and examples. So if you want to get some experience and build some prototypes, get into, yeah, maybe build even some robotic applications, you can definitely use this. If you have already some experience, or even if you don't, you can also start with STM32 platform. This is the one that I've been working with lately, and I find it very user-friendly because ST developed applications such as CubeMX and CubeIDE, which allow you to generate the initialization code. So all the low-level peripherals can be initialized automatically by these programs. So you don't have to struggle so much, with the registers and all that stuff. And what's even probably more important is that it's completely free. So you can buy like a board for real cheap and start doing really cool things. Furthermore, they have even very advanced tools which provide basically compiling machine learning models into libraries that can be imported into your microcontroller, and you can do pattern recognition and, well, depending on your microcontroller performance, a lot of things. So yeah, this is definitely a great, like very powerful platform to work with. Some other ones are also the has instruments. I haven't found. I tried to check, but I'm not sure if you can auto-generate low-level code for that. But they are also great. They make great microcontrollers. So feel free to check out that, and there is lots of courses on this platform particularly. Also, I should mention that microcontrollers perhaps 10 years ago and microcontrollers now are two different stories. Right now, you can have something like ARM, Cortex-M microcontroller based processors that have a lot of real-time, a lot of performance. So you can do, yeah, well, your limits are unbound almost. And in terms of growth, this is a very, let's say, it's not perhaps as fast growing as some other fields in computer science, but this is like a steadily growing area, and I'm pretty sure that in the following decades, it's only gonna go up because the number of IoT devices, the number of auxiliary systems, etc., are just increasing. So you can be sure that there will be a lot of work available if you choose to pursue this path. So I hope this has been helpful and give you at least some understanding about embedded programming and development versus typical, let's say, software development, where you aren't really, you don't really need to know that much about hardware at all. And if you have any questions, feel free to ask me. I would love to answer those. Thank you.
I have a question. So what actually got you interested in embedded systems?
I think I remember actually like nearing my graduation, and I was still like not sure what I wanted to do. But I've always been fascinated with, like, first of all, I have like my first degree was in electronics, so I always liked electronics. But then I, of course, realized that the future, I mean, the software development world is growing exponentially, and I thought it'd be great to combine both. So my interest in embedded in electronics and software, which led me to embedded systems, basically.
Pretty good. So I had another question. So how would you sort of run machine learning models on something so sort of like limited, like an embedded system? Like it's kind of like, right, you know?
Can you repeat that, please?
So you talked about how you could sort of like run machine learning models, right, on embedded
Yeah,
systems. Yeah, like
exactly.
how would you sort of run it on there? Because I believe it would be like really, really slow because it doesn't really have as much memory or like the hardware specifications.
Well, yeah, it's a great question, because you are 100% right. You know, it's a very constrained environment. So what they did at ST is they made this software that optimizes machine learning, let's say, models. Say you make a machine learning model that classifies, I don't know, like different. Like, let's say you're working with your phone and you want to know if you're running, you're walking, you're sitting. So you can first train that in your PC, and then with this software, you can actually put it in a small microcontroller. So it will reduce the number of layers, number of nodes, but still keep your, perhaps accuracy can go down a few percent. It depends, but it will successfully run on something small like microcontroller. Or, I mean, of course, you can also do it yourself. And if it's not a large, if it's a small, size net, you can even put it yourself in the firmware. But I mean, with this tool, it's super easy. So I think it's also like super cool for some of the projects you guys could do in the future if you want to get into this. So you essentially, there are lots of tutorials on this, where they actually show you like all the steps how to do this, and you can do this entirely like in Keras, or just like purely in Python, and have it like transformed it to like a very small net for a microcontroller.
I have another question. What advice would you give for someone who's like trying to get started in embedded systems, but is still a bit hesitant?
Yeah, I would say to think of some interesting project that you would be interested to do, and just go ahead and try to make it. Get some Arduino, get some. It should be fun. It should be about creativity and fun, and like you shouldn't like pressure yourself. Like I need to like learn all this stuff, all these registers. Just yeah, like make small steps, and have fun. And yeah, I guess that's the best way.
So thank you for that presentation. Unless anybody else has any questions, I guess we could sort of wrap it up.
Okay. Thanks, guys, for listening to the presentation. It's great to connect with you. Wish you a great experience ahead.
Thank you so much.
Thank you.
Everyone's free to leave now.
Sorry, what did you just say? I didn't hear.
Oh, I just said everyone is free to leave now, since the presentation's over.
Okay. All right. Bye, guys.